Okay, so I was discussing this Hopkinson's method or back-to-back test for determining the efficiency of two identical DC machine. So here initially what we have to do, we have to start the machine 1 as a motor by supplying rated voltage, and then we have to uh, adjust this rheostat to brought up its speed, to bring its speed at rated value. Okay, sorry. Okay, so so initially machine 1 is running as a motor at rated speed. Now machine 2 is coupled to this motor, that is machine 1. So its rotor is also rotating at rated speed. Now if we change the field current by varying this rheostat, then we can adjust the induced EMF value. Okay, so initially potential of this point and this point are not same, because potential of this point is actually the potential of the this point, which is the supply voltage. But since the generator is not initially generating any voltage, so this potential is at a lower potential than that of this one, and these 2 points are connected via this voltmeter V2, and it will record the difference, potential difference of these 2 points. Now by adjusting this resistance value, we can increase or decrease the field current. So thereby adjusting this rheostat, we can adjust the field current such a way that this potential of this point and this point becomes equal. Okay, so when potential of this point and this point becomes equal, at that point we can see the voltmeter of voltmeter V2 will read 0 voltage, and then we can close this switch S. Okay, so now the situation is, this generator is inducing a voltage which is equal to the supply voltage to the motor. Okay, this is called uh, the floating condition for this generator. Okay, floating condition means it is neither taking any current to the supply, nor it will taking from the supply, nor it is giving any supply, I mean current to the supply. Okay, so it is just generating as much voltage as applied to the motor. Okay, that means this generator is not loaded now, so it is not taking any load current. Whatever voltage is induced or generated by this generator, that is exactly equal to the voltage applied to the motor. Okay, now we can load this generator by increasing the field current of generator, or by reducing the field current of the motor, or by doing both. Okay, so in that case what will happen if we load this generator by doing either of these two or doing both? That means increasing the field current of generator or decreasing the field current of motor, or by doing both. In that case a current will flow, I2 current will flow through the armature of generator, and in that case this motor will drive the generator as it was driving already, and now the generator is also giving supply to the motor to drive, to rotate it, rotate. Okay, so what is the meaning of this? The meaning is that the motor is driving the generator, as well as the generator is also driving the motor. That is why it is, this method is called regenerative method. Okay, whatever power is generated by this generator, that drives the motor, and the motor also drives the generator. Now in that case, what is the function of this supply now? If we remove this supply, what will happen? In that case, due to the presence of different losses, this motor speed will fall. As the motor speed falls, the rotor will also rotate with lesser speed or lower speed, so its induced EMF will also reduce. In this way, gradually both the machine will stop. Okay, so that means this supply is required to supply the losses occurring in both the machines only. No power is taken from this supply by this motor to drive the generator or the generator to drive this motor. No power, extra power is taken from this supply. This supply voltage is now supplying only the losses occurring in both the machines. Is it clear now?
Yes, sir. Yes, sir.
So this supply is also required after loading this generator. We cannot remove this power, this supply voltage. Okay, this motor is driving the generator, so generator is generating some voltage or generating some power. That power is used to drive the motor. That means it is the power which is generated by this generator is used to drive the rotor of the motor. Okay, only. So whatever losses are occurring in these two machines, those losses are supplied by this voltage source Vt. Okay, so in this situation we have to record all the instruments readings. Okay, so let us see what are the readings we need to determine the efficiency of these two machines. So first of all, we have to record the armature current of the motor, which is I1. We have to record the armature current of generator, which is I2. We have to record the two field currents, and also we have to record the total current, that is taken by this taken from the supply, that is recorded by ammeter A1, and also the supply voltage Vt, which will be recorded by this voltmeter V1. Okay, so two armature readings, two armature current readings, two field current readings, and the current taken from the supply by these two machines. Actually, current will be taken, the total current will be taken from by this motor only, and the terminal voltage. Okay, so total current I supplied from the mains as recorded by the ammeter A1, then generator armature current I2, this current it will be recorded by ammeter A2, motor field current IF1, which will be recorded by ammeter A3. Next, generator field current IF2, which will be recorded by ammeter A4. Supply voltage Vt, which will be recorded by V1. Now with these readings, we need two other parameters also. Those are the armature resistances of two machines. Okay, R1 and R2. Suppose R1 is the armature resistance of machine 1, which is acting as a motor, and R2 is the armature resistance of machine 2, which is acting as a generator for this test. Okay, so we have to measure this R1 and R2, and these two has to be hot resistances. That means when the machines after the machines are used for performing this test, immediately we have to take these two readings, R1 and R2. Okay, you know that these hot resistances are slightly greater than that of the cold resistance values. Okay, So these are the readings we will be requiring to determine the efficiency of these two machines. Therefore, motor armature current I1 is equal to, if you apply KCL at this point, you can see this current I as well as I2. This is I2 actually. So I and I2 are entering current at this point. So I1, this current is I1. So I1 is the motor armature current, which is equal to sum of these two currents, I and I2. So motor armature current I1 equals to I plus I2. Motor armature circuit copper loss. So once we get the armature current, we will be able to calculate the armature copper loss. That is I1 square into R1. R1 is the hot resistance of this machine 1. Generator armature copper loss, we know generator armature current is I2 and generator armature resistance is R2. So generator armature copper loss is I2 square R2. Now power drawn from the supply by the two machines excluding the field circuit losses of both machines is equal to V1 into I. Why we have excluded this two field circuit losses? Because you can see the field circuit currents are taken from this point. This is field current taken from the supply, and this is another field current for machine 1 or motor. These two currents are taken before this part. So whatever happens here, that is independent of these two field currents. Okay, so the power input to these machines excluding those field circuit copper losses is equal to Vt into I. Voltage applied across these two, this machine is Vt, and current through this point, entering through this point, is I. So Vt into I is the power drawn from the supply by these two machines for different losses. Is it clear?
Yes, sir.
So this is the power input. Vti is the power input excluding the field circuit losses for both the machines. Therefore, total iron and rotational losses for two machines, if you subtract the two copper losses, that means the copper losses in motor as well as generator, if you subtract those two losses from this Vti, that is the total power input excluding field copper losses, you will get the total rotational losses, that is core loss plus windage and friction loss. Okay, so total iron and rotational losses per machine, this loss is for both the machines, so you have to find losses per machine, that is equal to, that is W0 is equal to half of this. So this is the total rotational losses, that is iron loss plus windage and frictional losses. Okay, so for a motor, now input power is equal to Vti1, that is the power input to motor, and motor armature, and field circuit loss, that power is also taken from the supply. So total input is armature input plus field input. So this is armature input, this is field input. So this is the total power input to motor. Now losses for motor, Wm. So that is W0 are core loss plus rotational losses, that is windage and frictional losses. This is copper loss and this is field circuit copper loss. So these are total losses. So once we get the input and losses, we will be able to calculate the output. So this is the output. Therefore, motor efficiency is equal to this output minus input. This is the input and this is the output. If you put the value of PIM here, you will get this expression. PIM and WM, you will get this expression. So this is the expression to calculate motor efficiency. Here all the quantities are measurable quantity. Vt I1 you have recorded, R1 you have measured, IF1 you have recorded, W0 you have calculated using the other readings. Okay, any question up to? So next is for generator, how to calculate the efficiency. So output power is Vt I2. In case of generator, I2 is the outgoing current. It is giving this current I2 is supplied to the motor, so that is some kind of output, and Vt is the terminal voltage of the generator also. So Vt I2 is the generator output, and losses we have calculated. This remains same for both the machines, only you have to change the copper loss. You have to calculate the total losses. W0 is same for both the machines. You have already determined the expression of W0. Copper loss you have calculated, or you have written the expression, and VTIF2, that is the field circuit loss in the generator. Okay, so this is the total loss in case of generator. So here G subscript is used to denote generator losses. Okay, so therefore input is this output plus losses will give you the input. So this is the input, therefore generator efficiency is output by input. So if you put the value expression of POG and WG, you will get this expression. So that is the efficiency of generator determined from this back-to-back test. Any question? No question. Okay, tell me, is there any advantage of this method over this Swinburne's test, or any disadvantage?
Sir, advantages like in Swinburne test, we are performing the efficiency in no load condition, but here it is in
Yes.
load condition.
So we don't know what will be the performance of the machine when it will be loaded. Okay, that is one advantage of this Hopkinson's method. Any disadvantage of this method?
Sir, we need two machines, two DC machines to perform.
Two identical machines. Identical is important. Okay, that is a major disadvantage of this method. We require two identical machines. Okay, so let us move to the next topic, that is torque speed characteristics and speed control of shunt and series motors. Okay, so our syllabus includes only speed control of shunt and series motor. Now before speed control, we have to consider these torque speed characteristics of series as well as shunt motor. Okay, so first of all, let us consider the operating characteristics of DC motors. So why do we need to know the different operating characteristics of DC motor? Because different types of DC motors will show you different types of characteristics, and depending on these characteristics, they are suitable for different types of applications. So that is why you must know the different types of operating characteristics of these DC machines. Okay, now normally we supply a fixed voltage to DC motor for its operation. So the parameters of interest for these DC motors are speed, torque, current, etc. Okay, as terminal voltage is fixed, so we are not interested about that. So if we consider these three parameters, so what are the possible characteristics? How many characteristics we will have if we consider these three parameters only? Tell me. Characteristics means plot between any two parameters. So what are the possible combinations?
Three, sir.
Three: speed torque, speed current, and current torque. So speed armature current characteristic, torque armature current characteristic, and speed torque characteristic. Now out of these three characteristics, we have only speed torque characteristic in our syllabus. Okay, so we will consider this speed torque characteristics only. So let us consider shunt motor first. Shunt motor connection, we know the field winding is connected in parallel with the armature. So whenever any voltage is applied to this armature of this shunt motor, the same voltage is applied across the field winding, and since we are keeping this supply voltage constant, so the field winding voltage across field winding remains constant with the variation of this load. So field current remains fixed, so the flux is fixed for a shunt motor. Okay, if we change the load, only armature current will change. So the equations or the relations between different parameters of DC motors, which will be requiring for this for a better understanding of this speed torque characteristics, we can write here, that is back EMF can be expressed in this way, that is EB equals to Pn phi Z by A, or we can write it P capital N phi Z by 60A, and that is equals to Ka phi omega m, where K equals to Pz by 2 pi A. This is a constant, it is known as armature constant. Okay, so back equation of back EMF will be required to understand this operating characteristics of DC motors, that is speed torque characteristic of DC motor, and this is the induced EMF equation using the machine parameters. Okay, and this equation is circuit equation of induced EMF. It is expressed in terms of terminal voltage and armature current and armature resistance. Okay, so this equation we can get applying the circuit theory law. That means if we apply KVL around the loop, then we will get this equation. Okay, and this is the speed equation combining these two equations, this one and this one. Okay, if we put EB is equals to K phi here, then we will get this expression. Speed is equals to Vt minus IaRa by Ka phi. And we have another equation, that is the torque expression. So T is equals to Kt phi Ia. We know that this Kt and Ka both are same from the magnitude point of view. Their dimensions are different, that means units are different, that we know. Okay, so we can combine these two equations to get the torque speed characteristic. Okay, this torque speed characteristic is also called mechanical characteristic. and under steady state conditions only it can be obtained using the equations I have shown in the previous slide. So equation 1, that is the speed equation, and this is the torque equation. So if we combine these two equations, that is replacing the current in equation 1 from this equation, then we will get this expression. In this equation, no armature current is there. We have replaced the armature current by T by K5. Okay. Now after rearrangement or simplification, we can write this Vt by K5 minus Ra into T by K square phi square. Now as I have mentioned earlier that for shunt machine, flux phi remains constant. Vt, that is the supply voltage, that is also constant. So this term is actually a constant value. Okay. Here in this second term, Ra is constant, K and phi both are constant. So what type of equation is this?
Y equal to mx plus c.
Yes, y equals to mx plus c. So this is an equation of straight line.
Straight line.
Okay. Will it pass through the origin?
No.
No, because c
No,
is
sir.
not equals to 0 here, isn't it? This is our c value, which is not 0. So this straight line will not pass through the origin. Okay. So what will be the plot for this equation? So let us assume this value. Suppose at t equals to 0, when the generated torque value is 0, still we have this amount of speed. So that we call it, that is called the no load speed. So that is why it is denoted by the symbol omega m0. Omega m is the speed of the motor and omega m0 is the no load speed. That is why omega m0. So omega m0 is equal to Vt by Ka, that is no load speed. Okay. So the characteristic based on this equation 3 will be like this. So omega m0 is a constant value. Now if torque increases, this value increases, that means we are subtracting some increasing value from a constant value. This is the line which is showing the constant no load speed. Now when torque increases, we are subtracting some increasing value from a constant value, so the line false. So we will get a characteristic like this. Okay. Now here two lines are shown. One is speed torque characteristic when armature reaction, AR means armature reaction neglected, and another is considering armature reaction. Uh, so due to armature reaction, there will be a slight decrease in flux value. So if we consider that value, I mean if we consider that armature reaction, then this speed will fall slightly with a higher rate than that of if we neglect the armature reaction. That means if we consider the flux constant, whatever may be the armature reaction is. Okay, so in that case we will get this characteristic, and if we neglect armature reaction, then we will get this characteristic. Is it clear?
Yes, sir.
So any question up to this? Okay, next is series motor. That is torque speed characteristic for series motor. For series motor, the performance equations are these equations remain same for both machines, but the circuit theory equation changes a little bit. Here, with armature winding resistance, we have to include the field winding resistance also, because both these windings are in series. Okay, so total voltage drop will occur across the armature winding as well as field winding. So this is the voltage drop, total voltage drop. Accordingly, the speed equation is equal to omega m is equal to Vt minus Ia into Ra plus Rec, that is the total resistance of the armature circuit and field circuit, divided by Kfi. Torque equation remains same, but here phi is not constant because the field winding is connected in series with the armature. So if load changes, the armature current will change, therefore field current will change. So we can say that phi is a function of armature current. Okay, so we can write phi as C into Ia, where C is a constant. So if we replace this phi by this Ca, we get this equation. So KAC Ia square, or Ia is equal to root over Te by KC. Okay. So omega m is equal to Vt by K phi. This we have already. So if we replace this phi by C into Ia, then we have this equation Vt by KAC Ia minus Ra plus Rac and KAC divided by KAC, because one Ia will get cancelled out. This Ia and IAC, that Ia will get cancelled out. We have Ia here, so we have to replace Ia by the expression that expressed in terms of torque and other constants. So you have to replace this Ia by this equation, root under Te by KAC. So we have this equation. So tell me, what type of equation is this?
Exponential decay.
No. Yes, exponential decay, but it has some other name.
Parabola.
Damping. Damping.
What is the name of the curve? Name of the curve?
Hyperbola.
Yes, rectangular hyperbola. Xy equals to c square. This is the equation for a rectangular hyperbola, isn't it?
Yes, sir.
Okay, so we will have a rectangular hyperbola type characteristic. Okay, so here if we neglect saturation, we will have this characteristic, and if we consider saturation, saturation and armature reaction neglected, that is the, yes, that is the palm line, and if we neglect it, that is the dotted line. Okay. So speed torque characteristic for a DC series motor is a rectangular hyperbola. Any question? Okay, no question. Okay, let me ask you one question, that after observing these two characteristics, that is characteristic torque speed characteristic for shunt machine and series machine. Can you suggest some application where these two machines will be applicable? I mean, suggest some application where we will be using this series machine, and suggest some application where we will be using this shunt machine.
Sir, shunt machine where we need the application of constant speed application, like the speed decreases in shunt machine curve is very slowly. So
Okay, and series motor. See, observe this characteristic of series motor very carefully. When the speed is very low, what is the value of torque?
very high.
Yes, that
Sir,
means
for high starting torque.
yes. So any application which requires high starting torque, for that kind of application, series motor is the best choice, isn't it?
Yes, sir.
Yes.
Oh, yes. So in this way, while you will be reading this topic from a book, you must see what are the applications of this series motor and shunt motor also. Okay. Okay, saturation part I have already discussed. Okay, so our next topic is speed control of DC machine. We have only speed control of shunt motor and series motor. Now, before we start this speed control method, we need to know certain terms related with this speed control. So, first term is base speed. What is this base speed? This is actually the rated speed given on the nameplate of the machine. Okay. Rated speed means what? When some rated voltage is applied and the field current is also rated, having rated value, in that case the motor will rotate with certain speed. Okay, that speed is called the rated speed. Okay, so speed control means, now what do you mean by speed control? Speed control means intentional variation of speed of any motor or of any device or machine as per our requirement. Okay, you know one example very well, that is the fan regulator. Why do we use a fan regulator? Because depending on the weather condition, sometimes we require high speed, sometimes we require low speed. So that is speed control. But with the change in load condition, if the speed changes, that is not included in speed control method. Okay, suppose some car is moving with constant velocity. Okay, uh, without having any passenger. Now if you put heavy load on that car, then the speed of that car will reduce slightly. If you give the same amount of acceleration as that of the previous one. So in that case, the this reduction of speed of that car is not included in speed control procedure. Okay, speed control means variation of speed, intentional variation of speed as per our requirement. Is it clear? What is speed control? Clear or not? Hello?
Yes, sir, please.
Okay, now that means while we will be controlling the speed of any motor, either we will increase or decrease the speed. Okay, so we need some reference value. Okay, above which we can increase the speed or below which we can decrease the speed. So that reference speed is the base speed or the nameplate speed or the rated speed. Okay. Now the speed regulation. Regulation, you know, voltage regulation you have learned in transformer chapter. Regulation means change in something. Okay. So here's regulation means change in speed with respect to this base speed. Okay. So percent speed regulation is equals to delta m. So delta m is the change in speed. So what is this change in speed? Is actually it is the no load speed minus actual speed divided by rated speed. Okay, if you multiply this by 100 you will get percentage. If otherwise it will give you the per unit speed regulation. Okay, now the constant power drive. Okay, so this is our base speed. So this y-axis shows torque as well as power, and the x-axis shows speed, and this base speed. So when we multiply this torque and speed, we will get the power, isn't it? Recall the expression EBIA is equals to TE omega m. So if we multiply torque by this speed, we get this power. So both EB and IA both are power. This is electrical power, this is mechanical power. Okay. So P is equal to TE into omega m. So torque into speed is power. Now here for below base speed, the product of torque and speed will give you this power line, and above base speed the product of torque and speed will give you this power line. So below base speed the torque is constant, which means this, when any machine operates below rated speed, it will form a constant torque drive, and above base speed it will form a constant power drive. Okay, drive means motor control which drives some mechanical load. So below base speed the load will be driven under this constant torque zone, where it will consume power following this curve. That means if speed varies within this zone, for this speed the power will be this, like that. Okay, but for this zone it will form a constant power drive. Okay, so constant power drive and constant torque drive, these are two possibilities. Okay, time is over. Today up to this, we will continue this speed control in the next class.